So classifying and quantifying acid strength. We will use this to figure out how to do calculations of pH, but we will have strong acids and weak acids. A strong acid is something that ionizes completely. So 100% ionization, which means it splits up 100%. You put it in, it does not stay as the proton with like connected to the original molecule, it completely splits up. So we essentially describe this as a complete forward reaction. The equilibrium constant is much, much greater than 1. I've got an example, right? This generic HA, where A is whatever the anion is. HA reacting with water, big regular forward arrow turning into H3O plus and A minus. It is 100% the products in this reaction. So there is no HA in solution. It is all H3O plus and A minus. There are 6 strong acids. I think there are 7 strong acids. I have 6 on here for you to know. I mean, I'll tell you the seventh. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid. The one not listed is chloric acid, and then sulfuric acid, but I've got a big note. Sulfuric acid is only strong for the first ionization, and I have the reaction written here. We'll deal with the second ionization later in this module. These are all of the strong acids. So the reason that this is important will show up when we do calculations, but right, it's just that set of 6 or 7 strong acids. That's it. If it's not one of those, then it's a weak acid. And weak acids exist as equilibria. So those equilibrium arrows are showing up because the acid was a weak acid, which just means that it doesn't dissociate completely. So HF plus H2O would be in equilibrium with H3O plus and F minus. There is still HF in solution. And for weak acids specifically, like yes, this is an equilibrium, that equilibrium is going to lie to the left. It will be mostly unionized HF and just a little bit of ionized HF. So a question you might have, if you didn't have this question, now I'm posing it to you, is like, why are some acids weak and some strong? We will go way more in depth with structure and how that affects weak versus strong acids. But the generalization is that after the ionization, if we're looking at everything kind of together in this big reaction mixture, the H plus and the A minus can either stay apart or get back together. If H plus and A minus don't want to get back together, they stay ionized. So getting back together, really, it means what is the strength of the attraction between H plus and A minus? So if it's a weak attraction, there's no incentive in getting back together. They stay ionized. It is a strong acid. And it also means that the conjugate base of that acid is a weak base. If the attraction between H plus and A minus is strong, so if they really want to get back together, they do. So the acid is considered weak. The conjugate base is considered strong. Now, these are very general descriptions of strong and weak, which I realize is maybe unfair because we're defining strong acids as 100% ionized. We're defining weak acids as not 100% ionized. But there is still a scale of strength. So within this category of weak acids, some can be stronger than others. So on this, like, why are some weak, why are some strong? You can have small amounts of attraction that the result is a weak acid or the result is really technically a strong acid. But what this is saying is look at everything that's happening in the reaction and in the system. If I have an acid, it ionizes, and those two things are perfectly happy to stay apart, they're going to stay apart. And the way that I talk about the strength of that acid is influenced by whether or not they stay apart, and that's what we're going for. Now, this all results in this thing called the conjugate seesaw, which I can show to you mathematically also at some point. But what it means is that the stronger the acid, the weaker its conjugate base, and vice versa. It is also a scale, right? You can have some acids that are so strong, their conjugate base is so weak. It is so weak that it does not act like a base. So it can be so weak that it produces a neutral solution, and we will have to deal with that. All right, we quantify acid strength with something called Ka, and I have great news. You already know how to quantify the strength of an acid. A stronger acid is one that has more of the dissociated ions. Well, if you look at the reactions for writing these dissociated ions, and you wanted to write an expression that told you how far to the right each reaction went, you would end up with H3O plus times A minus over HA. Kind of looks like an equilibrium constant expression to me. So Ka, it is the equilibrium constant for something acting like an acid. Larger Ka, more product, stronger acid. Okay, water can autoionize. I realize I have a great big ol' introduction to everything here. We're going to go into details, but you need some definitions. So we did see that water could be an acid if it reacted with NH3. It was a base when it reacted with HCl. Even when water is by itself, it does this reaction, but it reacts with itself. So we call it autoionization. So you start with water, but the product that you get is H3O plus and OH minus, or if you're writing it without the extra water, you get H plus and OH minus. You can do an equilibrium constant for this reaction. Water is a liquid and doesn't show up in this expression. We call it Kw because it's an equilibrium constant. The W stands for the autoionization of water, and this expression is concentration of H3O plus times concentration of OH minus. And it's a constant, right? It's an equilibrium constant, and we know the values of it. So Kw at 25 degrees is 1 times 10 to the minus 14th. So really small, which you would expect. It's mostly water in water, not the H plus and OH minus. But because they have to be equal to each other, you can find the concentration of each of these by taking the square root of Kw, which gives you 1 times 10 to the minus 7th as the concentration of OH minus and the concentration of H3O plus in pure water, which, right, we have not written the equation for doing pH yet, but if you remember that pH is the negative log of the H3O plus concentration, well, the negative log of 1 times 10 to the minus 7th is 7. That means that it's a neutral solution. All right. Using our definition of acids, if we have an acidic solution, the concentration of H3O plus will go up in that solution. But the dissociation constant still applies to the water. So we're talking about autoionization of water because if we know the H3O plus, we can also find the OH minus. Or if we knew the OH minus, we could find the H3O plus, as long as we know that it's in water and that it's officially technically at 25 degrees. So because of how that expression works, right? Kw was a constant and it was equal to H3O plus times OH minus. They're inversely related to each other, right? If the H3O plus goes up, the OH minus concentration goes down and vice versa. So let's look at an example. If a solution has an H3O plus concentration of 1 times 10 to the minus third, find the OH minus concentration. Well, H plus times OH minus is equal to 1 times 10 to the minus 14th, right? Kw, definition of autoionization, plug in the H3O plus value that I have. It means that my OH minus has to be 1 times 10 to the minus 11th. So overall, if we're thinking just about the concentrations, in an acidic solution, the H3O plus concentration is greater than the OH minus. In a basic solution, the H3O plus is less than the OH minus, and a neutral solution is one in which those two concentrations are equal. All right, so I have some practice calculations here for using Kw. You can take some time to practice with this, right? If I've given you H3O plus concentrations and asked you to find the OH minus concentration and then determine if the solution is acidic, basic, or neutral. You can do the determination by comparing H3O plus and OH minus. And right, I will leave this in here. You can pause, do the calculations, and then check your answers. All right, so quantifying this, we use the pH scale for quantifying acidity and basicity. So pH is the negative log of H3O plus, or you might write it as negative log of H plus. In general, at 25 degrees Celsius, less than 7 means acidic, greater than 7 means basic, and equal to 7 is neutral. So a few things to keep in mind. One is that the pH scale is logarithmic. So a change of 1 pH unit means a 10x change in the H3O plus concentration. The other thing is that, right, this scale, usually we talk about pHs between 1 and 14. The scale goes between 0 and 14, but those are kind of what we normally see in products and things that we use and things that exist, but those are not the only pH values available, right? You can have an H plus concentration that is so high that you have a negative pH. You can have a solution where the H plus concentration is so low, you have a pH greater than 14. There are also other p scales. So like p is a function. It just means take the negative log of whatever thing is listed. So POH would be the negative log of the OH minus concentration. A pKa would be a negative log of a Ka. So the POH will be helpful when we find base concentrations and try to find the pH of basic solutions. And if we use our Kw expression, we can set up the relationship that pH plus POH is equal to 14. So we get a conversion that doesn't require doing multiplication and division with powers of 10 that you might not be comfortable with. You can just use pH plus POH equals 14 if it's 25 degrees, which will be most of the time. pKa, it's a much faster way to report a Ka, because if we have a Ka, that's right. If the Ka were 1 times 10 to the minus 7th, then the pKa would be 7, right? That relationship there it's easier to report a 7. It's might be easier. You'll use pKs a lot in Orgo. It may or may not be easier to do some other calculations. I mean, it's definitely easier to do the equilibrium concentration or the equilibrium constant calculations that you will do in Orgo using a pKa instead of a Ka. Now we will probably use Ka the most because of the types of calculations that you're going to do with it. Just so that you can see some examples, I do have Kas and pKas for some weak acids here. Now, what's really nice about this table, it has the name, it has the formula, it has the structure, and it highlights which hydrogen is going to come off when it acts like an acid. What I want to draw your attention to, there's a Ka column and a pKa column. So for chlorous acid, the Ka is 1.1 times 10 to the minus 2. If you take the negative log of that number, you get 1.96. Down the column, right, we go minus 10 to the minus 2, 10 to the minus 4, 10 to the minus 4, 10 to the minus 5, 10 to the minus 5, right? We are varying my acid strength, but generally going from a bigger value to a smaller value. So chlorous acid, it would be considered a weak acid, but it is stronger than benzoic acid, which is almost at the bottom, right? 10 to the minus second versus 10 to the minus 5. Look at the pKas though. Chlorous acid is 1.96, benzoic acid is 4.19, right? That, because of the log, that's an inverse relationship. So a larger Ka means a smaller pKa, and they both mean a stronger acid.